thanks for coming. Today, initially, Christopher and me wanted to present to you the challenges of distributed feature flagging, and we wanted to propose some solutions. Now it is me proposing that because Christopher is out for some family emergency, so we've prepared that together. So we both are from a company called Codecentric. We are IT consultants, and I'm also part of the Open Feature TC. And this is why I'm kind of into that project and how we came to this talk and the topic. Okay, when we talk about the problems of distributed feature flagging, first we have to ask what does distributed actually mean. And when we talk about distributed feature flagging, we're talking about using feature flags in a distributed system. And then the question is, what is this? And here I have the definition from Wikipedia, which is distributed computing is a field of computer science that studies distributed systems defined as computer systems whose intercommunicating components are located on different network computers. I guess this definition is kind of weird to most of us now because today it's used in a broader sense, because typically what we mean is that we have different components running on any amount of physical computers that might be distributed across the globe in the same data center, and it could be anything from just several processes to VMs, containers, anything like this. And these components typically have to interact with each other. It could be like some explicit message passing, or it could also be like implicitly working together. Some things that immediately come up to many minds that have already worked on the field of distributed computing are the fallacies of distributed computing, mainly brought up by L. Peter Deutsch, who brought them up in 1994, inspired by the work of Bill Joy and Dave Lyons' fallacies of network computing, and they were added an eighth one by James Gosselin in 1997. So these fallacies are fallacies because typically these are things people just assume out of their intuition when they first think about systems and distributed systems, which are not directly clear to them. And so people always have in mind, or always think that the network is reliable. Latency is kind of zero. We don't have to consider that. Bandwidth is infinite, so we can send any amount of data. We just have to send it. It says the network is secure, so it's our network. It should be secure. That the topology doesn't change. We know what we are running there. We know how the systems interact with each other. There's one administrator. That's typically not what's happened. So you think you know every of them, but then there's another one who doesn't know you. And then that the transport cost is zero and the network is homogeneous. Another thing coming to the mind pretty early then is the CAP theorem. It comes from database theory, but it applies to all these distributed systems we're talking about. And generally what this says is that we have three qualities we have to compromise against each other. And what it also says is that one of these qualities is not really negotiable, because when we think about the CAP theorem, we're thinking about a distributed system that is working and that doesn't have a problem. So we need partition tolerance, typically. And when we say we need partition tolerance, so that we need to have all the systems to be able to talk to each other, that all the system parts have to still work if they cannot talk to each other, sorry. Then we have to see if we want to have availability or consistency. We'll come to that later in a more practical example. Okay, to show you like the typical challenges that come up, we brought up some architectures that we thought of, and maybe as a preface, everything that we will have a look here can be architected differently. But in reality, sometimes we just have to do stuff on a system that exists. So when we look at this, yeah, we really had to challenge us when we prepared this, because we were always like, but why do we do it this way? It is like this in this reality that we are in here, when considering that, and it would be too much work to just re-architect everything to solve that problem. So the first one here that we see is the inconsistency during transactions. So in this case, we have a book printing service where you can upload some images, then you do like nice layout of that, then you can order it, print it, and then it's getting delivered to you. In this case, we assume that the old service is kind of getting outdated. It's not that performant as we need it, and also the quality of the new service better. And holiday season is up, and we want to bring in that new service. The problem here is that you can see that for this, we need the order service as an orchestrator who first sends this order to the book processing service, which does some stuff, generate basically the printable view onto that. And then we have to create the print job in the print service. And out of some reason, we decided to poll for finishing these jobs. The problem now is that when we switch the flag, we kind of have to, or we have, when we do it naively, we are just going to switch to the new processing service, and probably we will have some jobs in the old service, and we don't know what works. So for this job, for this print job service, we should know that when we define this as a transaction, when we need consistency here, we want to be sure that for every job we ask the right service. Okay, a bit easier one maybe is the availability. So in this case, we have a video streaming website that brings in the feature to stream 4K videos. The 4K videos are shown on the video streaming website, which is triggered or which is changed by a feature flag, can stream in 4K. And we also have the video directory, which then gives you the representation of the videos you are entitled to see. And it also it's also changed by this feature flag. And now, in this example, we assume that there is a network partition. So basically, the video directory cannot talk to the feature flagging service. We have to do anything. And so we decide to not give out the 4K videos. But some users are seeing it in the front end, and it might change, or it might create confusion for these customers, which we want to avoid. Okay, another one that we have is, for example, so what we can see here is that we have a web shop, and it has like a linear checkout flow. So when we do the checkout, we are first creating an order in the checkout service, then this kind of starts the shipping process, and then calculates the shipping cost, and we're going to get a quote. In this case, we want to understand more about what happens in the background, so we want to add some additional logging. The problem about logging is it can be quite hard to be sure that we don't log, for example, personal identifiable information, because maybe our logging system is running in a region where we are not allowed to bring in some personal identifiable information of another region or something like this. And so in all of these services, we want to know if for this exact request we should log PII. The problem here is that in the beginning we might just start by giving in the region from the customer. We give it in, and it works fine. It's great. And now someone comes up and says we want to do it based on the region from the IP address. So we want to have the static information, but we also want to have the dynamic information. The problem here now is that every of these services would have to implement sending this IP address. It would first have to get this IP address maybe. It would have to go to send this then to the feature flag service, and it could just happen that some of them forgets that, and we have like different behavior then that we don't understand maybe. So when we talked about consistency, it made sense, or it was a good thing for us to think about two different kinds of consistency. So one consistency, which we see as the strongest kind of consistency in feature flagging, is what we call value consistency. In value consistency, we define that the downstream flags and the downstream evaluations should come to exactly the same value. So in this case, we ignore changing context because changing context might change the flag value evaluated. But sometimes that's not what we want. Sometimes we just want that all the services are having the same rules, but if they give something else into the function, like into the function of what value we want to get out of it, we want to get another value. And so we have kind of an intersect in the middle, because when I have rule consistency and when I have the same context, this creates value consistency again, because then I just have the function, I'm sure that I put the same inputs parameters into the function and I get the same output. Okay, so then what we thought about was how can we now get to more consistent feature flagging for downstream services. So in this case, what we can see is a diagram of how we imagine a concept called a flag set version. So we define this as a strongly monotonically increasing version ID for this flag set, which simply means we have a number that only increases, which helps us identify that we are either still consistent in the downstream service, or that if we have a network partition, if we cannot talk to the feature flagging service, that we are inconsistent because we know the number that we got is higher, so we assume we have a problem with the number that we got. So in this case, you can see, like, first we are evaluating the flag, and in the result we are getting something we call flag set 1 here. So flag set 1 in this case is just this monotonically increasing number that I meant. And we have a downstream service, and the downstream service actually caches the flags, because this is something we want to do for getting higher availability, because then we don't always have to talk to the flagging system. When we get the flag set, we also get the flag set back, and in this case we can actually see that the flag set we got back was flag set 2. So probably something has changed in the meantime. And then we do the downstream HTTP API call, and what we do here is that we propagate this this flag set ID that we got back when we did our initial request to the flagging service down to the downstream service. In this case, we chose to do it via baggage headers in HTTP because we are using HTTP here. And then we are evaluating the flag again, but we are sending the flag set ID from above because we noticed that our cache must be, or that our cache is actually newer than what we used, so the rules might have changed. Exactly, and now as this happens, this second service, as you can see, is actually implemented in a way that it caches the flags, and so we get that. What we get out of this is first what we call the rule consistency. And rule consistency can here be always ensured when there's no network partition between the downstream service and the flagging service. If there is a network partition, so the downstream service cannot talk to the feature flagging service, at least we can now detect that we are not consistent with the upstream service anymore. So this is something that might actually be better for us. So in this case, we only have to trade availability, so we should do anything that we think is sensible, then over the consistency. Okay, another thing we could do, which we also had in the discussion, was that we could just propagate the whole rule set. So sometimes also what we see in the front end is that feature flagging in the front end really just uses something, for example, as we've already heard today, like JSON logic. This is also done for other providers, again, especially for the front end, because then we don't always have to call the backend services. And what we do in this case is, first, we are getting the rules. We are kind of evaluating in memory. And then when we do the downstream call, we just send the whole rule set down. So the good part about this is then after the initial rule getting, we are always just working in memory. And so what we can always ensure is rule consistency between the upstream and the downstream services. Also, we get the partition tolerance between the downstream service and the feature flagging because we just don't have to call them. It just doesn't matter. And we get availability that is not dependent on a feature flagging system. So the only availability concern we have is that the services can talk directly to each other. Now looking at our policies again, we can see that here in orange we marked bandwidth is infinite and transport cost is 0. Why? Because rules might get really large. And this is something that probably is something that speaks against the solution. Because if you consider in every HTTP package header sending all the JSON logic rules on something like this, it could become too much. For simple, small solutions, that might be a thing, but it might just be too much. And then the other thing is that the network is secure. We said that we want to propagate everything downstream to the downstream services, but sometimes, actually, what we don't know is if the rules are genuine. So are we sure that the rules only originated out of our system, or did someone just give us a rule set? How do we know? We have to find a way, if we want to do it this way, that only our rules, only the rules that we really want to trust are given to our system. Okay, something that's like orthogonal to that is we can also bring down the context. So as we've discussed earlier, when I have rule consistency and when I have consistent context, I actually get value consistency if I need it. So in this case, what we can see is that the upstream service does a feature flag evaluation, or actually two, one with context A, one with context B, and then it does the call to the downstream service. In this case, over the package, it sends its original context that it has used. And then maybe the downstream service does another call as here, and it actually adds its own context again, which is context C. And it does the call to downstream service 2, which now is the sum of the context A, B, and C. So the downstream service is actually like downstream service 2. It doesn't add any additional context. It's transparent to this. Something we might like, something we might not like, but at least downstream service 2 doesn't have to know which context has to be used. We just send it all downstream, and we don't have to change our implementations. We don't have to redeploy. We don't have to coordinate between the teams. So this is something that can work. Out of this solution, we can get value consistency. But it's not granted, because value consistency only works if the context is not changing during going down the chain. Because if we add another property, a rule might decide to do something completely different, to return something completely different out of there. And then we have some or many of these potential problems listed here. So it simply doesn't address reliability or latency, because in this case, we don't do anything for that. We've had it already. So bandwidth is infinite and transport cost is 0. They apply. So it might just be too much. It might be too much context to propagate, especially if we don't know how long our call chains are downstream. Sometimes we don't know. And then the other problem is that, or that we see here, is the network is secure and topology doesn't change. What do we mean by this? Topology doesn't change. It's important for us to know whom we are propagating to. We don't want to propagate to a third-party service. Maybe the context that it could be PII in there. It could be an email address. It could be anything. So we really don't want to send this to any third-party service we don't intend this context for. Okay, another thing that we could come up with then is flag value propagation. So when we really want value consistency, we could also just send all the already evaluated flags down to the system, down to the downstream service, which first, as we can see here, we are evaluating a flag A, then we are, oh, it's wrong, actually. But yeah, so we are evaluating flag A, and then we are getting back a result for that. And then we're doing that for a second flag. And then we just take these two flags, we send them downstream. And then we can see here we are just evaluating in memory, so we don't have to talk to the downstream service anymore. So we get, again, value consistency because we simply have the values. What we also get is availability, because we don't depend on the flagging service downstream. So downstream, it doesn't matter anymore if we can talk to that. That means that we have partition tolerance again between exactly these two services. So in this case, we kind of have consistency for the values. We have availability between the feature flagging service and the downstream service, and we have partition tolerance between those. So the only partition tolerance that we need to make sure, and availability if we need it, is between upstream and downstream. The problem again here is that bandwidth is not infinite, so it just might be too much again. So the network might not be secure, so we have the same problem as with the rules. So if we just take anything that is propagated to us, we don't know if we should really enable this feature for the person. That could be a problem. If I know maybe what to enable for me, it could become problematic. And then if the downstream servers have different context, they really have to decide what to do. If they have different context, maybe they can reevaluate the flag, or they don't. Or do I know that always? That's something I still have to decide going for this solution. We had the problem of the propagation several times now. So one idea we had for this was, couldn't we go for something like OpenID Connect for feature flags? And the idea here is mainly that we have some public key that our flagging system signs its flags with. So what we can see here is that we have the public key loaded by the upstream service, the downstream service, to just do that initially and be able to also work without the flagging service. And then we evaluate the flag. And in this case, we actually get a signature back. And this signature can be used when we propagate the flag. So imagine in this case, we are having what I just described, the flag propagation. And what happens now is that we are propagating this downstream, validate the signature, and we can be sure that our feature flagging system was the one that these values came from. The same works for rules. So actually, this works for both of these problems. And yeah. But again, this doesn't do anything about the bandwidth is infinite, topology doesn't change, and trend cost is 0. These are still problems we are facing, even when we have this solution. Okay, and then we asked, what could OpenFeature do if we refine these solutions, if we find any of these solutions needed, if we see that case? The first thing it could do would be to add the flag set version concept to the SDK and off-rep. So you can do that today. You can send back the flag set version in the metadata of the flag, and you can also send the flag set version in the evaluation context. But it could be something we can make more prominent. We can just have as a high-level feature, maybe also just as a pattern, something we can come up with to just have this as a generic solution. Another thing to enable what we've just talked about this is we could actually go and we could bring in our own JWKS endpoint into either off-rep, or we go further and we say this is a generic solution for all feature flagging services, and we try to get a well-known URL registered, which everyone could depend on, even though you might not even be using OpenFeature or off-rep. This could then be used by our SDKs to first, first like pack and sign, or like packing and signing has to be done on the provider side then. So we could at least help with defining how this should look like. Do we do something like a JWT? Many problems are solved there, like issuers, audience, and so on. So maybe we could just rely on that and we could pick that up. The other thing we need then, now that we have this format that is signed, we still have to validate this. So we can basically just add this functionality into our SDKs, doing the validation of the signatures downstream. And also what we could do then, if we want to propagate either flags or rules downstream, we could have the propagation via HTTP baggage or whatever works then for the specific system we want to propagate something to downstream. And then something really important is we would have to find out how we ensure these boundaries. We could be really conservative and we could like have a allow list to where to propagate. We could be we could also be like doing the difference, saying, okay, which network are we propagating to? This is pretty hard, and I'm really interested in if someone has an idea on that. So yeah, that's something we imagine, but we have not yet solved, and we don't have a finite answer to that. That's it.
Thank you, Lukas, not Thomas. Any questions on this?
Yeah, hello. So you gave us like a whole bunch of potential solutions. Do you have your own preference, which one you prefer?
So I think something that could make sense for us, kind of out of the box, would be adding the FlexSet version, because this is something that might be interesting for like many users, and it's something that doesn't really distract anything. So you can just add it optionally if you think you need it, and we could support that. And for the rest, I think we would really have to go into refining the solutions, look into the concrete implementations of that, all the edges that I didn't go into now. So, yeah.
Okay, yeah, cool. I was just wondering.
Any others? Nope. Okay, we'll be back in, about 10 minutes for my lightning talk on the multi-provider.